Swayam Prabha. Digital India. Educated India.
Okay, now why is this important, right, for optimization? Importance is basically due to this theorem. So let us say your objective function that you're trying to minimize is a convex function. Then any local minima, let's call it x star of f, is also a global minima. Okay, so we need not worry about this situation. We are trying to minimize f, so of course you would want to reach x0. Okay, but several algorithms, what happens if this is the kind of function you have, you will get stuck here at this point x star. Okay, and you will sort of have to do with this suboptimal solution. Okay, so in such cases, if this cost function f is convex, then you need not worry about such issues. You will always end up with a global minima. I'm not going to look at the proof, it's very simple, it just uses the definition of convexity. Of course, I'm going to share the slides with you, so later on you can look at the proof if you want. Okay, but remember this important result, which is why you always try to look for convexity in optimization. Okay, this is the reason.
Excuse me, sir. I have
Yes.
a doubt.
Go ahead.
Sir, what about the function f equals x cube? In f equals x cube, the point of the minima is the point of inflection.
Why do you call it minima? This and this, right?
Yeah.
There is no minima, right? It goes right up to minus infinity.
So the slope at 0, 0, I mean the slope at the point 0, 0 would be 0, right?
So, is there any other condition that you should check? So, if the slope is 0, does that mean it is guaranteed to be a minima?
You have a local minima there then, right?
So, if I take a look at this function, right, what do you think would be the slope assuming this is?
Okay, minima would not be the right term. Extrema would be the right term.
No.
In this case, it would be maxima.
Exactly. You can have a maxima, you can have a minima, you can have points. This is called a point of inflection. Right? It is neither maxima nor minima. That happens because the second derivative
is also 0.
Exactly. So this equals 0 is not enough to guarantee you a minima or a maxima. You have to look at second order derivatives.
Okay, thank you, sir.
Okay, so this is why convexity is important. The kind of optimization algorithms and conditions that we are going to look at, it depends heavily on gradient of a function, or basically the first derivative of a function. Okay, and gradient comes from differential of a function. I'm not sure how many of you are not aware of this. So differential of a function is basically doing a linear approximation of the function around that point. So if I have a function that looks like this, and if I take a look at this point, I want to, let's say, so the function is not linear, right? It is sort of maybe x square or x cube or something. It's definitely not linear, but I want to approximate the value of the function around this point as a linear function. Basically, geometrically, what you are trying to do here is draw this straight line with, right? So you can sort of make a tangent line, right? This tangent line described as a function is what is called the differential. Okay, so you may have heard of this word before. The intuitive meaning is you want to do a linear approximation of this function at any given point. Of course, differential can change to change the point. Instead of at x0, if I want to do a linear approximation of the function at y0, the tangent line or the straight line would be different. Okay, so it depends on point to point. But at any given point, the idea is you want to linearly approximate that function. And the notation is this. Pfx means at what point x are you trying to linearly approximate this function, and h is, so if I sort of deviate from this x0 by a small step, let's call it h, then differential of f at x with the value h gives you how much has the function, the linear approximation to the function changed, right? Once you have the differential, using the differential you can define the gradient. Okay, so gradient of the function at a point x, it's a, first of all, note that it's a vector. Okay, the direction of the vector, so the unit vector is along this perturbation vector along which this differential is maximized. Okay, so if I go back, so of course in this case there is only either this direction or this direction. There are no other directions, but of course we are talking of functions on Rn, right? So we have this sort of a situation. We have the domain is 2D more, right? And I want to find out at this point x0, y0, what is the linear approximation. So the linear approximation to the function would be some sort of a plane, right? This, and I want to figure out which direction should I move, right? So is it this direction, this direction, this direction, or this direction? Which direction should I move so that this tangent plane, the height of this plane increases the maximum? Okay, that is what is conveyed by the gradient of the function. Okay, and so this is the vector of the direction in which your gradient vector points. The magnitude of that vector is nothing but how much has this linear approximation changed. And remember, once I've already should emphasize here, I'm only looking at in what direction this linear approximation increases the maximum, not decreases. Okay, which is why, of course, this magnitude, which must be non-negative, it will always be non-negative. Right, so that is the gradient. Question, dimensionality of the tangent is always n minus. So by tangent I mean I have to draw it. I have to draw it in n minus in Rn, right? So in this case, it's the tangent plane is a plane in R3. Remember, gradient vector is a vector that belongs to the domain of the function. Okay, so if I have a function f from R2 to R, gradient of f at any point x will be a two-dimensional vector. All right, but the tangent plane, of course, is also describing the change in the value of the function, which is why it is drawn in R3. Okay. So this was to give you an intuition. Of course, I'm sure all of you know this. Just take all partial derivatives, put it in a vector, you get the gradient. Okay. But what is important to realize is that there is a intuition behind this. The intuition is this. Okay. We are looking for a direction in which this linear approximation is maximum, and the magnitude is the amount of that increase. So that is gradient. Quick question. What happens to function values in directions which are orthogonal to that of gradient? How will the function behave in that directions? 0, right? Good. locally, in the sense that if I take a small enough step in directions which are orthogonal to that of gradient, right, then the function value will not change at all. Okay, and that comes up because of this. Right, the amount of change in the linear approximation of the function f is given by a dot product of the gradient and the perturbation vector. If h is orthogonal to gradient, this dot product will be 0. Okay, so if you go in directions which are orthogonal to that of gradient, locally, right, because remember, all I'm saying is the linear approximation does not change. It does not mean that the function itself doesn't change. Okay, so if you restrict h to be very small, then it's likely that the value of the function will not change at all. Okay, having said that, now let's look at unconstrained optimization. Right, so we are given a function f from Rn to R without any constraints. Okay, so we are supposed to just find the minimum x, the n tuple that minimizes this function. You may have hopefully heard of two algorithms, gradient descent and steepest descent. Let me quickly tell you what they mean. Gradient descent, you basically start with a random point xk, right? This is the direction, gradient. Okay, let's call it hk. Again, don't get confused between hk and h from the previous slide. Right, hk, I'm just calling it, it's a new notation, just take it that. hk is the gradient of the function f at the point xk. Right, why is this important? It's important because gradient of the function at xk is giving me an idea that maybe if I look in this direction, the value of the function will increase the maximum, increase the most, right? Because after all, this comes from a linear approximation. It's not coming from some wild other function. This gives me an idea of this is the direction in which I should look if I want to increase the function maximum. I am going to look in exactly the opposite direction, which is why you have a negative sign over here. So if I look in the exactly opposite direction to this hk, I'm likely to reduce the value of the function the most. Okay, so I'm fixing this direction, or basically the negative of this direction, and then all I'm doing is I'm searching that if I stick to this direction only, minus hk, how much should I go in this direction so as to minimize the function? Okay, so that is a different optimization problem, but the difference is it's a smaller optimization problem. Smaller in the sense that this is a one-dimensional optimization problem. Okay, because I'm only looking for this step size. How much should I move in this direction so that I end up with a minima along this direction? After I have found out what is the step, I take that step, okay, and I obtain a new estimate of the minima. Then I just check, is this a satisfactory minima or not? There's different ways of doing that. Then maybe look at how much have I changed from the previous estimate. If I have not changed for several iterations, if I'm sort of moving around in the same place, maybe this is a good enough estimate of the minima. So let's stop. Maybe I can look at has the function value increased, right? Or has the function value changed much? If it has not, then stop. Okay, but if not, then you repeat the step. So at this point xk plus 1, I will have a new gradient, therefore a new direction to search for, and I repeat this process till I satisfy the stopping criteria. This algorithm is what is called steepest descent. You should think of this algorithm as if, let's say you are on top of a hill, right? And your visibility is restricted, maybe due to fog or whatever, and you want to get down to the base camp at as rapidly as possible. So let's say you can look only 2 meters around you. So if you look at the area around you in a radius of 2 meters, you maybe pick a direction in which there is the most descent, right? The height decreases the maximum. Okay, so you then go in that direction, you reach a new point, again you have a new area which is visible. That area you again look for a direction in which you think there is the most descent, the height reduces the maximum. Again go at that direction and repeat. Okay, more popular version of this is called the gradient descent, in which you are basically lazy, so you do not perform this one-dimensional optimization at all. You just choose some small step to take in that direction. Why does this make sense? Because HK is obtained from the linear approximation. So as I said, if I ensure that I take a small enough step, then the linear approximation does describe the function around it quite well. Okay, so as far as you choose a small time step, this strategy will also make sense. Okay, so you have gotten rid of this one-dimensional optimization problem. And there are several algorithms that will help you perform this optimization as well. But for now, let's not get into that. Okay, so then, okay, let's move ahead. Another method, another variant of this is what is called the Newton's method. You may have studied Newton-Raphson root finding method. So this method is based or derived from that particular concept itself. The search direction is the only thing that is different. Search direction is now not only dependent on the gradient, it is also dependent on the Hessian of the function. I hope all of you are familiar with Hessian of a function. Okay, so that is the only difference here. So this is sort of an overview of unconstrained optimization. Let's look at constrained minimization, which is sort of which has found several applications in shape modeling, geometry processing, machine learning, image processing, etc., etc. Right. So again, just to get you back to where we were, this is how a non-linear constraint optimization problem would look like. It will have equality, inequality constraints, set constraints, everything. Okay. So let's first look at only equality constraint minimization. Okay, so you are given only one equality constraint h from Rn to R, and you are asked to minimize the function f such that the point of minima satisfies hx equals 0. In this picture that you see, all these red ellipses, they are sort of defining curves on which the value of the objective function is the same. Okay, so on this particular ellipse, the value of the objective function is everywhere C4, okay, where C4 is some number. On this ellipse, right, the value of the function is C3, C2, C1, so on and so forth, and maybe let's say this point is the point of minima globally. But of course, you are not supposed to find this point because it does not satisfy the equality constraints. So points that satisfy equality constraints are represented here by this black curve. Okay, so you should restrict your search for a minima only to points on this curve. Right. So now let's try to figure out what is the condition that the minimum point on this black curve will satisfy. Okay, so if I take a look at this point x1, right, since this curve represents points where h is 0, right? In what direction would the gradient of this h point to? Although I have drawn it over here, but intuitively, what does that mean? Gradient of h, again remember, it points in a direction in which the function increases the maximum. Basically, you can think of it as if this is a curve h equals 0, there is a, so maybe I'll draw a separate picture here. This is my x1. I can have a tangent to the curve here. Then this gradient of h will be basically orthogonal to the tangent. This tangent, this is my gradient of h. Does that make sense?
Yes, sir.
Okay. So this is the gradient of h shown in black arrow. At this point, the gradient of f, of course, will also be in this direction, right? Because you can see this point lies on this ellipse. I can draw a tangent to the ellipse, something like this. The gradient to the f will be perpendicular to this tangent. What does that mean? Means that this gradient of f, right, I can go a little bit along the curve in a direction that is aligned with this gradient. If I go in that direction, then what happens? The value of this function will of course increase. And similarly, in this dashed arrow, which is just negative of the gradient of f at x1, if I travel along the curve a little bit along this direction, right, I will still ensure that I am on the curve only by taking a very small step. But the thing is, I have traveled along the negative gradient. That means in that direction, the value of the cost function f has to decrease. Since there is a point which is sort of around this point x1 at which the function value decreases, therefore this point x1 cannot be a point of minima. Right? A point of minima is a point where no matter in which direction you go, as far as you have a small step, right, the value of the function cannot go below that. That is what is a point of minimum. So let us look at this point x star here. This point, the gradient of f points in this direction, the red arrow. Gradient of the constraint function h points in exactly the opposite direction. In this case, I can either move in this direction or in this direction. But by moving on this curve in any of these directions, is the value of the function going to change? Right? Both these directions are characterized by, these directions are orthogonal to the direction of the gradient of the cost function. And we just discussed, by going in directions orthogonal to the gradient of a function, the value of the function doesn't change. Therefore, this is your point of minimum. And what is the characterizing nature of this point? That the gradient of h, right, the equality constraint, and the gradient of the cost function, they have to be aligned. Either they are in opposite direction or are in the same direction, it doesn't really matter. Right? Maybe the function value h increases in this direction. In that case, the gradient, this black arrow, would have been drawn in the opposite direction.
Excuse me, sir.
Yes.
In the diagram, why is gradient of f at x at the point x star? Why is it pointing
This way.
horizontally? Yeah.
Yeah,
Shouldn't
because
it be tangent to the
this red ellipse.
Oh, okay.
See, these ellipses are points where the value of the function is constant, does not change.
Oh, okay, sir. Sorry, I got confused between the two
So that's
curves.
okay. That's okay. Does that make sense now?
Yeah, yes, sir.
So the conclusion here is the point of minima x star is such that the gradient of h at x star and gradient of the cost function f at x star, they are aligned. They are either in opposite direction or in the same direction, whatever. Okay, so that is the condition. Although I have not done linear algebra before this, but I hope you understand that that implies the same thing as saying that this vector gradient of f and the gradient of h are linearly dependent.
Sir, so for a single, so basically what we're doing is for a single value of the cost function, we're looking at multiple values in the level surface of the function f,
Right?
and we are trying to find the minimum most value of f,
Exactly. So the actual
like
picture
at a particular level surface. I mean, at a particular level surface of the cost function, we're looking at multiple level surfaces of f, and we're trying to find the value of uh, the minimum value of any of those level surfaces of f.
right. So it's like this picture in R3. If I look at this picture from top, then I get this picture.
Okay. Yes, sir.
Okay. So conclusion is that these two vectors, they are supposed to be linearly dependent, which means that one can express one vector as a scalar times the other vector. So which is what is this equation? Gradient of f plus some number lambda star times gradient of h must be 0. And the important thing here again is this is a concept where a lot of students get confused. This lambda, right? It is a unique number, cannot be any number, right? You are trying to express one vector in terms of the other vector, right? So since these are two specific vectors, this lambda also has a specific value. It cannot have any random value you like. This specific value lambda star, hopefully some of you may have heard this term. This lambda star or the variable lambda is what is called Lagrange multiplier. Right? And the condition that x has to satisfy if x is a minima is this. Okay, so let's now just rewrite this. So we define a new function called the Lagrangian. It is a function of two variables, x and lambda. Define it in this way, fx plus lambda hx. Then if x star is a local minima of this equality constraint minimization, then the gradient of, or basically the derivative of this Lagrangian with respect to the variable x must be 0, right? Why? Because gradient x, Lx star lambda star is nothing but fx gradient fx star plus lambda star gradient hx star. This we already intuitively proved that this must be 0. The second condition, the gradient of this function with respect to lambda evaluated at x star lambda star, what is that going to give you? Right? What happens if I differentiate this with respect to lambda? Just get h. Okay. This basically says that the point x star must satisfy the equality constraints. So these are what are called the first order necessary conditions. Now we have worked with one equality constraints. You can extend this to m equality constraints, h1 to hm. We are going to make one assumption. The assumption is that the gradient vectors of all these m equality constraints are linearly independent. What does this physically mean? Simply means that these m equality constraints are in a small neighborhood around that point, are sort of independent of each other. They are not just reiterating the same condition that some other equality constraint has already put. Okay, so for things like, let's say this is one equality constraint, this is, oh, sorry, I should draw it over here. Like this. This is another equality constraint. At this point, both the equality constraints would have the same gradient, right? Locally around this point, there is absolutely no difference between these two equality constraints. If I look at a small neighborhood, so we are not going to consider such conditions. We are always going to assume that all these m equality constraints have m linearly independent gradients at that point. Such points are called regular points. Once that is done, then it's the same thing. You just have one Lagrange multiplier per equality constraints, and then you can just rewrite this as a vector fx plus the vector lambda transpose times hx, where hx is, again, if you recollect my notation, it is h for x, hx transpose. Whenever I write a vector, you should always assume that it is being written as a column vector. This lambda transpose would be a row vector. Then we just have same thing in general. First order necessary condition, if x star belonging to omega is a local minima, then it has to satisfy these two conditions, which are just a generalization of what we saw over here. What is this matrix? I hope all of you know. This is what is called the Jacobian matrix. And the Jacobian matrix would have the gradient vectors of each function in the rows. So keep that in mind. JHX star would look like this. The gradient of the first would be over here, gradient of the second would be here, gradient of the mth. Okay, and then, so this is just a first order condition. So I think somebody had raised this point whether x cube at 0 is a minima or not. So just by looking at the first order condition, we cannot guarantee that it's going to be a minima. But of course, if it is a local minima, then first order necessary conditions are going to be satisfied. So we need to also look at the second order conditions. Second order conditions means we are looking at second order derivatives, right? So the second order necessary conditions, I'm not going to derive it. Basically says that V transpose this second order derivative of the Lagrangian function into the vector V must never be negative.
Okay. Okay. So then it reaches the minima.
Yes.
Because it's convex at the point.
Yes, exactly. Yes.
Okay.
Second derivative being positive means it is like a bowl.
Yes,
right?
sir.
Upright bowl. And why we are sort of multiplying it by V? Because it's a constrained optimization problem, right? So main thing is, so at this point, the entire Hessian in all directions need not be non-negative. I am only worried about what happens with second order derivatives in this direction only, because these are the only directions in which I am going to remain in my constraint set.
Sir, so it's more like a dot product. You're looking at the projection of.
Yes, yes. So V transpose Hessian V. So this would just be one number.
Okay, this is a similarity transformation.
No, this is not similarity transformation. It's basically a matrix. This is the Hessian of Lagrangian, right? V transpose would be this vector times V, something like this. So 1 times n, n times n, n times 1. This has to be non-negative.
Okay, sir.
In an unconstrained problem, we would just say that the Hessian of f must be greater than equal to 0. That is an overkill. That is all I'm trying to say. In an unconstrained problem, I can go in any direction I want. I would still be in the feasible set. In this case, I cannot go in this direction and obtain a minima. That's pointless. So I should look at how the second order derivative behaves only in these directions.
Okay, sir.
Okay, that is what this means. I think it's a good time to take a break, maybe. Yeah, it's 11:17 as of now. I hope I have not put all of you to sleep. So I think we'll get back at 11:25 maybe. Okay.
Sir, I have a doubt, sir.
Yes, go ahead.
Sir, about the gradient descent, sir, you said that alpha value is heuristically determined, sir.
No. That is, yeah. Okay, go ahead. Yes.
Sir, can we change the alpha value each iteration and determine like how fast it's approaching the minima?
Yeah. So alpha k, you can choose yourself. You can vary it in every iteration if you want.
Okay.
So typically you will see, I mean, some approaches they usually take alpha k to be sort of half of the norm of hk, something like that. So hk is a vector, right? It has both direction and magnitude,
Yes, sir.
right? Hk is the gradient. So at some points, so if I take a look at this sort of a function, right? At this point, xk, the gradient, which is the first derivative in this case, has a very high value.
Okay.
Right? So slope is high, basically. That's all I'm trying to say. So if I use the same alpha k, let's say alpha k is fixed to 0.5, that means I'm going to take a very large step in this direction. And I may sort of miss the minima.
That's going to cause what's called overshoot, right?
Right. So you need to sort of carefully select alpha k as well. So if I sort of do something like this, I'm sort of normalizing the step size with the gradient magnitude. If this gradient magnitude is very high, I should be sort of careful. It's like you're going down a hill. If the descent is very steep, then you better take small steps. But if the descent is very sort of is not too steep, something like this, then you sort of can go, you can take a longer step in that direction. All right.
Sir, is it possible for you to make the slides available to us after the lecture gets over?
Sure, I'll do that.
So that we can
Definitely.
refer to the slides and like go through it again.
Yes, surely. I'll
Thank
make
you
that
very much, sir.
available.
Thank you.
Thank you, sir.
So, yeah, 5 more minutes. So please, we meet at 11:25. Right now it is 11:20. Yeah, so I'm not going to go into the proofs for the second order necessary conditions. Again, I hope the intuition is clear. Would want, if it's a minima, second order derivative must be positive there. The only thing here is we need not have second derivative positive in any direction. Because some directions it's forbidden for you to explore in that direction. Simply because it would violate your equality constraint. So only those directions in which you are not going to violate the equality constraints, in those directions you should be worried about the second order derivative.